Hello everyone, for this video. In this video we are going to discuss chapter 5 and 6, which are forces and motion. These two chapters will be divided into three videos, part 1, part 2 and part 3. And this one we are going to start part 1. At the end of the three videos, actually, you should be familiar, and at the end of this chapter, you should be familiar with Newton's first law, forces and mass, Newton's second law, the gravitational force, which is the weight, the tension force, the normal force, the friction force, Newton's third law, and properties of friction and uniform circular motion. Newton's first law. We are all familiar with the Newton's first law, which tells us that if no net force acts on a body, the body's velocity cannot change, that is, the body cannot accelerate. In other words, if there is no net force, if the object is at rest, it will remain at rest, and if it is moving, it will continue to move with the same velocity since there is no external net force applied. Force and mass. We all know that a force is measured by the acceleration it produces. Additionally, we are all familiar that the force is a vector quantity. What do we mean by vector quantity? We mean that a vector quantity has magnitude and direction. This means that when we have two or more forces act on a body, we can find their net force by adding them vectorially. What do we mean by vectorially? It means that we need to take the magnitude and direction into consideration, as we learned in chapter 2. This principle, actually we call it superposition, principle of superposition. The mass of the body is the characteristic that really relates the force body by the resultant acceleration, and we are all familiar with this. Now, Newton's second law, this is very important for us, which is Newton's second law. The Newton's second law tells us that the net force on a body is equal to the product of the body's mass and its acceleration. As you see, F net equals m times the acceleration. Important here is to emphasize that when we talk about the force, we are talking about the F net. F net means that if we have multiple forces act on an object, we need to take all forces into consideration. To solve problems using the Newton's second law, it is really more convenient to divide them into three directions, which means that if net along the x-axis equals ma along the x-axis, if net along the y-axis equals the mass times the acceleration along the y-axis, and if we have F net along the z-axis, so it is equal to the mass times the acceleration along the z-axis. However, actually most probably we would not have forces along the z-axis, but if we have, we can take it into consideration. To solve problems with Newton's second law, it is also often to draw the free body diagram. So what do we mean by the free body diagram? The free body diagram is the net forces acts on the object. Here is an example to explain to us the principle of Newton's second law. Part A, B, and C of figure below show three situations in which one or two forces act on a buck. The mass of this buck is 0.2, it is given to us, and the three forces is given to us if 1 equals 4 Newton, if 2 equals 2 Newton, and if 3 is 1 Newton with an angle of 30 degrees, as it is illustrated in the figures or in the situation. Here actually again this is the situation number 1 or situation A, where we have only one force along the x-axis. Here is the situation number B, where we have two forces. One is along the positive x-axis and one is along the negative x-axis. And situation number C, we have two forces. One is along the negative x-axis and one is along the XY plane directed with an angle theta, and this theta is given to us as 30 degrees. Let's solve it together actually now, considering situation number A. Situation A, as you see, so we have only one force, so we simply apply the Newton's second law, which tells us that the force equals ma. Just substituting in this equation, we get that the acceleration along the x-axis equal the force divided by the mass. The force is given to us as 4 newtons, and the mass is 0.2, so simply we can get the acceleration is 20 meters per second squared. Again, or also, since the force is along the positive x-axis, so the acceleration would be along the positive x-axis. So this is situation number 1. Considering situation B, where we have two forces, the first force is directed to the positive x-axis and the second force is directed to the negative x-axis. In this case, we need to take the net forces act on the object where they are here, F1 minus F2. F1 is taken as positive since it is to the right, and F2 is taken as negative since it is directed to the left. Please don't confuse that you write F1 plus or F1 negative negative F2, because this negative indicates that F2 is directed to the left hand. Substituting in this equation, we get the acceleration along the x-axis, F1 equals 4 minus 2 divided by 0.2, so the acceleration in this case would be 10 meters per second squared. Now, considering case number C, it is also similar to what we discussed previously. However, this F2 is to the left hand side, which would be negative. This is easy. However, for F3, we should break it to two components. This component, which is F3 cosine the angle theta, and this component is F3 sine the angle theta. Please review, take care that this is the angle, so the component which is adjacent to the angle takes cosine, and the opposite to the angle takes sine. So this component is F3 cosine the angle theta. So if we need to get the acceleration, again, the acceleration is given that F net divided by the mass. F net here is F3 cosine the angle theta, which is F3 1 cosine 30 minus F2, why minus? Because F2 is directed to the left, divided by the mass, and the mass is given as 0.2, so we get the acceleration. The acceleration, as you see, is negative 5.7, which tells us that the magnitude of the acceleration is 5.7, and the negative sign tells us that it is directed to the left. So this means that the object or the buck or the particle we study under situation C will accelerate to the left side. The gravitational force F equals mg, we are all familiar with this gravitational force, which we call it the weight. So the weight equals mg, and again we should recall that the gravitational force is always directed downwards. So the gravitational force or the weight is given by mg, where m is the mass and g is the acceleration. And again, we all understand that the weight has the same direction of g, since the mass is always positive scalar quantity. Now we are going to move to discuss three important forces. They are called contact forces. In this part of this video, we are going to discuss the tension force. Whenever we have a cord or we have a rope sometimes, or we call it rope or cable or wire or string attached to a body and pulled taut, there is a tension force, or there is a force in this wire or in this cord. We call it tension force, or simply sometimes we call it tension. The name comes that the cord is under tension. The name comes that the cord is under tension. So that's why we call it tension force. Take care actually that the tension force is drawn along the wire. As you see, whenever you have a wire, you have a tension force directed along the wire, as you see. if we have, for example, a wire directed in this direction, so the tension force also would be in the same direction. So this is the tension force. Here is an example for the. Now, taking the free body diagram of the traffic light, we can say that T3 minus mg equals 0, y 0 in this case because there is no acceleration. Signal force is equal 0 because this traffic light is at rest. It is motionless. It is in motionless situation. It is stationary. Here actually we can take this T2 and we break it to one component here. This component is T2 cosine the angle theta, since it is adjacent to the angle, so it is cosine the angle theta. And we have another component here which is T2 sine the angle theta. Taking also T1, T1 would be broken to two components. Here is T1 cosine the angle theta, and here is T1 sine the angle theta. Now in this case, looking to the free body diagram of this node, if you look to the free body diagram here, so what we conclude? Taking the forces along the x-axis. Now taking the forces along the x-axis. Here is the x-axis. We take the forces along the x-axis. So we would write that T1 cosine theta in negative plus T2 cosine theta equals 0. Or in other words, T2 cosine theta, since it is to the right, it will take positive. Negative T1 cosine theta. If we take this negative T1 cosine theta to the right hand side, so we can get a relationship between T2 and T1 as you see. T2 equals T1 cosine theta 1 divided by cosine theta 2. This equation gives us the relationship between T1 and T2, or the ratio between T1 and T2. It does not give us T1 or the value of T1, or it does not give us the value of T2. However, if we take the signal forces along the y-axis, now please look to the forces along the y-axis. So if you have a look along the forces along the y-axis, so we can say that T1 sine theta plus T2 sine theta 2 minus Fg equals 0. We took here these two forces as positive since they are pointing upwards, and the force which points downwards, we take it as negative. So we all agree now that all forces point upwards will be taken as positive, and forces point downward, it will taken as negative. So here is the equation for the forces along the y-axis. Again, why these forces or the net forces equal 0? Because there is no acceleration along the y-axis. If there an acceleration, if the object is in motion, so we need to write equals ma. Solving these two equations, so